plant is that you start with the scheduling and planning, where you set up production targets and feedstock allocation and whatnot. And then you get back to the site-wide optimization, which is some real-time optimization that is done, but not necessarily real-time all the time anyways, but it's done actually. And then you have local unit optimization, but primarily where you have most control engineers is between supervisory control and regulatory control, of course, this layer down there. And of course, set points and optimized outputs sent down across the chain of command, actually, in process control. So basically, that's what you have. So we'll look at the Tennessee Eastman process. Tennessee Eastman process is a very popular process in chemical engineering. In fact, it's the benchmark process introduced by Downs and Vogel in 1993. It's similar to one of the Shell plants in Tennessee, basically. And of course, it consists of several units, 5 units specifically. The reactor, the condenser, compressor, and of course a vapor liquid separator and a stripper. And then of course you have several recycle streams, and it can be as complex as this, but this is like a model just to give us like a platform where we can test our control strategies, especially in process control. And of course this is guided by some reactions, AC, it's generic, so there's no specific reaction, especially regarding the chemistry. But it's good to know where you have 2 given products, G and H. And of course, you have this inerts, basically, or unwanted gases in the plant. And of course, you have several reactants. The reactants, of course, they cost money in every plant, actually. And then you have about 5 major units, like I said earlier. And the plant is highly nonlinear, unstable, overload unstable. And yeah, we'll be looking at that plant today. Just to give us an idea of what the Tennessee Eastman process looks like, this is exactly what it looks like. This is the P and ID diagram of the plant. You have several units. Like I said earlier, you have the reactor, you have the stripper, you have the condenser, and you can see there's a lot of things going on here, a lot of non-linearities going on here, and that's that actually. And of course, the full process, like I said, it's a benchmark process. So what we try to look is, when we look at the variables, you have 6 modes of operating a plant. Usually, if you go to a refinery, there's several, there can be several modes or production factory. You can have, for example, the Tennessee Eastman process operates on 6 different modes, actually. 4 to 6 are maximum production rates. But 8, which is what we're considering, just the first 3 modes are based on the quality of what we produce in our plant. Basically, we have about 50-50, which is the G to H ratio, 10 to 90, which is low B, and C, which is 90 to 10. And of course, you have different flow rates, and depending on the architecture, you can have several of them. And these are basically the manipulated variables in there. And you have, just to mention this, 41 measurements are basically used for, 41 measurements, we have 41 sensors that you can get data from the plant. And of course, this is the cost function, which is our primary interest here. So basically, we're running an operation, 72 hours, 24 hours. How do we find, what are the metrics we use to define our cost of operation? Every plant has this. You need to keep track of how much you're using to produce. So basically, Downs and Vogel introduced this, and this is running strictly based off your purge. Your purge is basically the amount of when you recirculate within the plant, you send out some important, you are trying to purge out some inert gases, and when you do that, you purge out some, you purge out some important reactants as such. And of course, you have the production rate, and then you have the cost of steam, and then the cost of your energy within the plant. Now, this is the cost of each and every reactant we have in the plant, and of course, the cost of running a compressor, and of course, the cost of steam. Now, pay attention to this. We are strictly considering operating costs. Some literature might consider profit, but we don't, because every plant has different metrics for profit, and you can't necessarily base it on a particular profit. That's like guessing. So we stick to Downs and Vogel's problem specifically. Okay, so Downs and Vogel has been introduced since 1993. So of course, there's been several control strategies, several PID architecture introduced to that. So you have different PIDs on that. So different PID, architecture around that actually. So for the sake of simplicity and access, we have access to the RICA, decentralized PlantWide control. He designed his PID architecture in 1996, and we'll be basing our simulation based on this plant actually, and we're working on what RICA already did since 1996 actually, but now we'll be focusing based on economics. Now, this is basically RICA's plant-wide architecture. I'm not going to go into the details, it's in the reference, but a brief detail is to know that we have a production set point, which we use in getting our production index. Our production index, you have several ratio control loops, and then you have several override loops, and you have several PID loops there, and pressure loops there actually. So basically, that's that on that, and for much more information on how the PID and the regulatory layer works, It's down in the reference, and we can check that as we go. So basically, just to give us a deeper insight, I'm working with MATLAB Simulink. This is basically the plant we have. You can see several set points around here, and we have, this is basically the PID loops, and we have a cost block that calculates how much we run the plant, especially when there's disturbance, when there's no disturbance, and for different scenarios actually. Sorry. Okay. Sorry. All right. So just to, before we get to where we're going, it's best that we know where we stand currently with the current architecture. How good really is Rika's plant? Now, basically, we carried out some statistical analysis, and then we introduced some disturbance, and then we calculated what is when there's no disturbance in the plant, the ideal case, what happens, how much for each mode, what is the cost of running each operation? And then you can see that from the first, running the cost of operations is about $5,000 for running after 3 days, basically. And then you have a mode B and then mode C, and then you can see this are just the baseline reference. And then you can see that when we have a disturbance, particularly IDV2, which is a set of disturbances you have according to the Rika's, according to Downs and Vogel's disturbances, you can see that the cost when there's a disturbance, it skyrockets down from $5,000 to about $8,000 and $11,000 and $3,000 for different modes, basically. And of course, this, what drives the cost basically are none less than either the purge composition or purge flow rate or the compressor work or what have you, based on the cost that we're calculating. Now, this is just to give us a further insight into this. You have mode A, which is how the plant functions when there's no disturbance on an ideal case scenario. And these are for the 3 different modes. And you can imagine when there's a disturbance, when a disturbance hits, you can see the plant is economically unstable. And any, of course, the CEOs who owns the business, this is not acceptable. You're basically running, on a very, very bad slippery slope on that one. All right, that's just to give you an insight into the problem, the literature review, what are the current literature review we have. I went down, I selected literature back as, down the lane when the problem started, just to, give us an insight, but not to, we're just gonna focus on what we're trying to do, which is basically the economics. And one paper that I make reference to a lot is the paper by Totlayer and Codran in 2020, where they developed a multi-stage EMPC, where they had to vary the disturbance between plus or minus 20, 20, that was just a number given, very percentage of every process variable that he had, and tried to develop some multi-stage MPC for that. That worked out, but the reality is that in every plant, you can't have a variation of, there's no law that says every disturbance will be between plus or minus 20% variation. So you have to consider a real world scenario at large. All right, so that being said, we're just going to look at the problem statement and the research objectives, pretty straightforward. The TEP problem, like I said, operates on 3 distinct modes, 50-50, 10-90, 90-10. An existing plant-wide control structure, although stabilizes the plant, but it's economically suboptimal or fragile when the mode changes. Another thing you want to consider is that when you switch from mode A to mode B, because every plant you run, you don't run on one particular mode all through. I might be producing kerosene with a particular quality, and I want to change quality tomorrow, depending on the market demand or whatever. So basically, you have that, and then you have about 3 different modes. And the gaps in the literature, of course, like I said, this is lifetime architecture. It's stable, but economically compliant, especially to IDV2, as we saw earlier. Classical EMPC, they only did this on 1 mode, and then you can't basically generalize that for every other mode. MultiObjective, like I said, is studied for small subsystems. Surrogate MPC, we'll get to that in a second as to why, because when you have a very, very large nonlinear model, you want to be able to replace that with some surrogate model that will work as in case. So the research aim is pretty simple. Develop a unified, computationally efficient multi-objective plant-wide optimization and control framework for the TEP process that integrates EMPC and evolutionary optimization with surrogate modeling, basically. It's a pretty large one. And then, of course, we divided, of course, the first objective here is to modify and validate the TEP simulation, which we've done, design and implement the EMPC layer, which is the current phase we are in, formulate the multi-objective problem, which is the phase that we are about to proceed into, and of course, to develop the surrogate model, which is for the modification of that. And basically, we'll look into the methodology. Now, just to simplify things and to make things a lot more easier, we developed this block diagram that synergizes a unified architecture that integrates not just regulatory control, but also integrates optimization as well as multi-objective goals into this actually. And of course, from the block diagram, you can see here, we have the baseline PlantWide control, and then it goes to, we try to get a model. Now, we are using a NAX model. We'll get to that in a second. Even though the topic says mechanistic, but we'll get to why mechanistic didn't work out in the end. And of course, when you have an EMPC layer, you want an EMPC layer that's functional, that works, and then that can, operate the plant, optimally in some given sense. And then over time, you want a multi-objective to be able to run the plant on 3 different objectives, depending on what the plant or whoever is in charge of the business would prefer actually. Maybe he's trying to prioritize profit, energy, or or quality, depending on the objectives. And we'll see that in a second. Now we shrink that into just 3 architecture. You can see that we have the Tennessee Eastman process, and then of course you have the economic nonlinear MPC, and then we have the multi-objective optimization, which you can see that we split it into 3 objectives basically: profit, energy, and robustness. And that's that on that. Now the methodology is into 3 phases. Phase 1. Data collection and system identification. Phase 2 would be EKF, extended Kalman filter, EMPC formulation, which is the stage we're in, and the last and final phase will be the multi-objective phase with integrating surrogate modeling as part of the goals of the research itself. So we start with phase 1, data collection and system identification. This is a very integral and major part of this thesis. Data collection is something skillful, because in an industry you're never allowed to perturb more than 5%. So it's a very handy tool, especially when it comes to getting data from the plant, and of course identifying a model. Everybody in control engineering will agree with me that identifying a model that really captures the dynamics of your process is a very tedious job, and of course it has to be done with good precision. So before we start, we consider 3 different models: a mechanistic model, because linearized state space model, non-linear state space model, polynomial models, and of course a data-driven model. Now, mechanistic model, one of the issues we had with it was that since we're dealing with only primarily economic variables, we cannot, there was no direct relationship from the literature, and it will be difficult. It's almost impossible to get a direct relationship with what Rika has designed with the economic variables. So we considered it, but it was not adopted. Linearized models, of course, they were good, fast, and you can use them for EKF estimation. But overall, they weren't as good as much, because we couldn't have a good fit. And even when we had a good fit, it wasn't. We couldn't use it for economic optimization at some point. A data-driven model, we made use of NAX modeling. This is nonlinear autoregressive modeling. It captures the nonlinearity, trained on closed-loop excitation data. And of course, FMICOM with our solver was pretty good, and we had great results with that, and adopted that for the economic prediction engine, which is what we did. Now we consider the sample time of 1 hour. Why? Because every process in chemical engineering most processes in chemical engineering are very slow processes. It takes about 20 hours to settle. So if your process takes about 20 hours to settle, when you run the calculations, you would see which is the number of prediction horizon times the settling time, greater than or equal to the settling time. We were able to come on. Calculations are not shown here, but they're much more in the report as such. So excitation and design. Sorry, forgive me for this, but basically, we use a round-robin staircase design. Perturbation, basically. This is basically associated with the computer systems engineering. The idea is from there, but not necessarily. It's not necessarily. It's adopted for MIMO perturbation, basically. And what is that? You basically just going to explain from here. You basically just divide, the points you're trying to perturb into strata. Strata is just levels, which staircase levels actually. And then you run them into rounds, and then you have different seeds for them, and then you perturb them at, simultaneously, basically. And that alone captures the dynamics of the system. And mind you, pay attention, we're not going through all the variables, we're just looking at economic variables at that, because we are trying to make sure that, our plant, the decision in our plant is determined by the economics of the plant, basically. So of course you have 2,800 at nominal, and then of course you have this as the range, and then we have several perturbation range. We have about 8 levels of strata, 8 divisions for each 10 set points. And of course that took us about 2.5 hours to dwell. Dwelling time is just how long you hold on for every set point. And of course over the hour for running the entire simulation, 72 hours, so that you have about 207 hours for each, because we conducted about 5 experiments, so that's like 1,000 hours per mode of active perturbation. And although we cannot show for every mode, there's a lot of results. So basically, this is basically the result. So you can see that for this is perturbed simultaneously. We held that at different times. And of course, you can see the data. This is the operating cost we got at some time. You can see it's between 100 and then 100 and $300. Sorry, that's a mistake. $500, $800 actually. And of course, you can see other variables well captured. And this is repeated 5 times again for mode 2 and mode 3, so we can get the dynamics for that. So in the end, system identification is another thing which is very important. Like I said, several other system identification methods were considered, but primarily we got, we were in a pickle between 2 different models, either a sigmoidal nonlinear finite impulse response model, or a nonlinear autoregressive model, which we're using, the algorithm was Levenberg-McQuartz, and then we switched to a NACS model, but instead of Levenberg-McQuartz, we're using the Bayesian regularization. And of course, at the end of the day, Bayesian regularization proved to be, the best among all the model, and then we'll see that in a second. We tried with sigmoidal, we can only capture about 8 variables, and then diverge when we're using Levenberg-McQuartz because it's fast, it gets to an optimum, but it might be a local optimum, not a global optimum, and then of course we couldn't get a good fit with that. So just to give us a simple, not too in-depth ideology of the NACS model is that you have a regressor matrix from your data, and then when you put that into your regressor matrix, you put that into a neural network, and then we train per mode. Now, you pay attention, we're using a MISO model. It's a multiple input, single output model. We couldn't use for the 3 modes basically, so which means we have 14 models per mode. So it's a lot actually, and there's a reason we did that, because when we combined all the modes together and tried to train for all the 14 outputs, we were struggling in trying to predict. And then you see the results of prediction down the slide, as you can see here. So we had, these are just the number of the arrangements in terms of the hidden layer, the activation function used, the solver used, and of course we had to normalize the data so that it's not heavy for the neural network basically. So basically, when we compared 2 best models we had at first, is a sigmoidal non-finite impulse response model, and then the NACS train Bayesian regularization model basically, and this is what it fits. And then you can see the differences. Of course, we're able to capture all cost variables, basically the compressor work, the flow of steam, the flow of the purge over time, and then the production. And of course, after running this is basically the summary of what we did. Basically, you have about 16 inputs here. Basically, it's a NACS modeling because we have to inject and shift inputs over time. So that's why we did it for the 14. It's a MISO model. So when you combine that, it's about 150 dimension models. So it's quite heavy on the network, if you ask me. So the EKF implementation and EMPC formulation, basically, just because you've done system identification doesn't guarantee that your model is exact and it will predict the exact same output. So what do? You have to, apply some sort of filter to it. Of course, that's the extended Kalman filter. Of course, this is just the steps for the extended Kalman filter. You have to predict with a NACS model, and then after predicting, and then you have to correct the covariance. And of course, we did that with a 72 dimension. The 72 dimension being every output actually. So we have about 14 different cases, and this is just the steps for extended Kalman filter. And then of course, these are the parameters we use for the extended Kalman filter. And we're not using analytical Jacobian basically. Just the central finite difference. And that alone is it was enough to carry out our prediction. And we'll see the results as we proceed down the slide. 14 EKF blocks. This is just a summary of the EKF. And yeah, the next is the EMPC formulation. So like I said, we're strictly using a supervisory, we're strictly using cost variables, no profit term. Because like I said, profit is generic. Any plant can come up with a different profit anytime. So we just stick with the cost of as the problem as it is. So basically what we have is basically the cost function, the cost of running the plant, which is part of your economic cost function. And you have the error between when you send out optimal set points from your EMPC, you want to make sure that the error is quite low. And of course you have the reduction term, which is in terms of you're trying to minimize, and we have some slack penalty, an L2 slack penalty at that. And of course you have the constraints, and then these are the decision variables at the set points you're trying to optimize. Okay, so this is basically the structure of it. You have the economic states cost, the tracking penalty, the move suppression. And the weight matrix this is basically the weight matrix. Now, if you pay attention here, you see we have a lot of weight penalty on the levels, because in PlantWide control, and when you check a lot of PlantWide control papers, you have to be able to stabilize the inventories. The inventories are basically your levels, your tanks. If you have perturbation, if you have your tanks not stable, moving up and down, you're not going to have a good, consistency when it comes to the feed, to the feed composition. Basically, you have oscillating composition. And so we want to make sure that we have stabilized. We don't want our EMPC to change the levels that much. Same thing with the A to C ratio of reactants. Heavy penalty on those. Heavy penalty on the production set points. And of course, heavy penalty because according to the papers and the literature, we don't want the recycle valve to open so much. So what we look at is basically the key drivers, which is the purge rate that is driven by the pressure, the temperature, and of course other variables. And this is basically your penalty in terms of the error. So we don't want much variation, and the rest will be in the thesis. Of course, this is basically the hard constraints considered. A lot of modification has been done. We'll try to move around Rika's own, so this has been corrected. It's about 28890. We'll try to move around Rika's optimal set point. Rika claims that 2850 is the optimal set point for running the plant in terms of pressure, because it gives a balance between purge. But so far, we'll see if that's true. Multi-objectives. This is the next phase of the project, but we haven't quite gotten there yet. But just to give a quick rundown of what it is, basically, you just multi-objective. You have a bunch of feasible solutions that were already been determined by the EMPC, and of course, you have an E point. And then these solutions, you're supposed to find some level of optimality in there. Of course, you have the Pareto front where you have some of them dominating, and we try to get some optimal set points amongst the solutions, but this hasn't been much. We haven't delved into this that much, but this is the whole idea behind it. And of course, we have 3 plant-wide objectives that we are looking into. The first is profit. Now, I know we said we're not considering profit, right? But to look at it in a different objective, to minimize the cost of operation, gives some sort of production index that you're maximizing profit. So of course, you can use that. The energy, of course, energy terms in the plant are basically your steam and the compressor, so you want to have an objective that minimizes this. And that robustness is basically the error. How good are you tracking? So, of course, you want to have a balance amongst all 3 solutions, and of course, to get a good Pareto point for that. So if we link all those 3 layers as a unified architecture, you can see that we have the EMPC close. Now, surrogate modeling is also going to come into the multi-objective layer as well. But the problem is that we need to finalize with stage 2, which we're currently doing at the moment, almost done actually. So we have that, and then of course, surrogate-assisted NSGA, of course, is basically just replacing the EMPC layer with some surrogate model just to make it fast, because even running the economic optimization itself is very, very, it takes a lot of time actually, because it's very heavy. The model, you imagine having 14 models, is actually quite heavy. So we look at some results, starting with the system identification for mode 1. We weren't able to present mode 2 and 3 results here because it's a lot of results due to time constraints of the presentation. So we look at the NACS validation models. You can see that our NACS identification with Bayesian regularization actually captures all the dynamics of the 14 economic variables, and you can see that here. And of course, we have now you might think, oh, it might overfit, but thanks to the Bayesian regularization, we have a good fit. Accurate prediction actually, and we'll see that when we actually predict with the models. And this is your NFIR, which we had to replace this, the Y3 with the NACS model eventually, because the purge flow was, we were having very, very, it was difficult actually. You can see from the way the data is presented, it was difficult to capture that at first, and so we had to do that, and then we had about 70 to 80 fits. And then when you compare them, you can see that for the NACS modeling with Bayesian regularization, we barely had anything less than a 98% fit. Of course, we had worse than that when we had the NFIR model. And of course, when we compare both of them, you can see that for the NFIR fit, you have a rainbow kind of fit, and then you have a very consistent 98 to 99% fit, and when you check the difference between them. But overall, the NFIR is still good, right? It still looks good. But the difference is when you actually predict, and you can see that from here. Now, what we did was take the true measurement of the baseline of the economic variables. So what did Downs and Vogel propose? This is what the economic variables, this is the starting point, and try to see if the model predicts it. And you can see that when we did that, we had very great prediction with the NACS modeling. And when you started with the NFIR, despite its good fit, you can still see that we had some variations in terms of what the true variable would be. We cannot use this basically. And of course, there are other methods, to try to see if we can improve that. So the EKF estimation, pretty simple. We wanted to make sure that our model were accurate. So now the plant runs at a sample time. Of course, it's a regulatory layer. It wouldn't run the same sample time as your filter or your EMPC because you're updating over a certain interval. And of course, for the you can see here that you have, we're doing it over 1 hour interval. So our Kalman filter predicts every 1 hour and updates every 1 hour, and then you can see that regardless of where you started off, they converge even with the sampling time of the process at 0.01 hours actually with the conversion. So basically, the EKF performance is pretty good. It's not presented here. We have the results in the thesis report for each of the modes, the state dimensions, and of course the state dimension, of course, several other parameters of the EKF. In conclusion, the NACS plus Bayesian regularization is superior identification method for the system for phase. This is for phase 2, for phase 1, and EKF closes the model gap reality basically, and the framework generalizes across the operating mode, but this is still to be confirmed. I need to make that that was a misjudgment for my part. So the economic model predictive control. So up until this morning, when I had a good result, at least a very a relaxing result actually. Up to this morning, basically, these were the parameters I used for my economic MPC. We had about we made a prediction horizon of about 4 hours, 1 hour for the control horizon, 1 hour for the sample time. And then, of course, for the decision variables, you have this at the set points you're trying to optimize, and we'll see the results in a second. And of course, this is our structure. A little bit scary, but there's nothing really. It's just some blocks put together, and then, of course, we can get some outputs. And this is basically the Simulink structure, and then we're using. So we can see the EMPC's tuning strategy. Like I said, these are the nominal parameters given to us by Rika. So when you're running optimization, you allow your optimization move from a known point, and then you direct it in the path that it will find an optimal solution to it. So the cost of running the plant at base strategy for per hour is about $100 an hour. And we'll see how our EMPC drives towards a much more economical, favorable position than what we have earlier from the base strategy. And of course, you have the reactor pressure bounds is between 2,850. We had to change that later on in our EMPC configuration. And we had tight level control, like I mentioned. You don't want your level you don't want an imbalance. You want a stable, and the first principle of PlantWide control, the inventories must be stable. And of course, so that you don't have varying composition. And narrow the temperature, of course, we had to narrow the temperature because Rika already gave us some hints, basically, as to where the optimal temperature would be. But you still have to, when optimization, you still have to, poke and poke until you can get something better. And of course, you have the production and recycle flow rate, and then we had to bound them to a very, very small range. And of course, before tuning or running our EMPC, what we try to do is economic sweep. Economic sweep is basically you try to run an optimization based off your model, and of course, you cannot manually calculate what the profit would be and get some optimal pressure range. So when we did that for pressure, we were able to, although from the literature, Rika already stated that when you increase the pressure, you get, good economic standing. But we did that first to just find out what would be the optimal pressure range and keep on, moving that as well. And when we did that, we checked, we verified with the decentralized control from Rika itself, without the EMPC, without the EKF. We tried to do that, and then what we had was that we had the mean cost for each of the pressure, and of course the mean cost we had was about 95.63 for the for the cost of operation actually. And after 8 hours we had about $100, and after final cost we had about $100.71 basically. Final purge rate was this, because purge is one of the things that we know that drives the cost. So very aggressive level. And when we put all this together, we found out that at 2,890 kPa, you have a good mean cost of operation actually from the decentralized control alone. And this is just from running an optimization where you have your input and output model. Basically, of course, key findings are there. So when we compare this again with the fixed baseline, like I said, this is the baseline from Rika. The mean cost was about 95.63 actually, and after 8 hours you had this, and then after final cost you had this, which is where it settled at. And of course, the current EMPC was able to, when we tried it with the current EMPC, we were able to push it about 90.4, and then we have some good values, and the rest is they say. Of course, now what we have here, these are those parameters for our tuning parameters for the EMPC, and this can be verified. It's in the slide already. So this is the current cost of operation. It's about $100 without any disturbance, without any tuning and all like that. Like I said, this is the current cost of disturbance. Basically, you can see the cost. We have this. Now you notice a large transient in here. Why? Because at the start of your plant, you don't expect to purge immediately. This will take some time, and of course you see the purge. When you start purging, you purge out expensive materials out of the plant, and of course you have a very high skyrocket. And you can see where it settles at about $100 an hour, above $100 an hour, about 101 basically. And that's what you have. And you can see this is the cost of running the plant basically, just for at mode A actually. And this is for 72 hours actually. So when we run our EKF, we were able to, although you have this is basically due to transients, of course, and then you can see that we have an improvement actually, an improvement. I wouldn't say it's optimal because we're still tuning to get, it's an improvement basically. And then you have this, and then once you have this, it's an improvement. And then when we check the mean cost, actually per hour, we had about $97.88 an hour, which is quite an improvement, but it's not necessarily the optimal improvement basically. And of course, this is where permit me, this is for a level basically, it's a mistake in the diagram. And of course, you have the product loss. This is the product loss, which is the loss at the stripper. And of course, you have the compressor cost, which is the compressor cost. Now, when we did our EMPC improvement, the compressor cost and the steam cost was as high as anything. It skyrocketed at early transient. And of course, these are the set points. So, like I said, the balance point is meet the set point, improve cost. Basically, is what you can see here. We met the temperature, met the pressure. Pretty good actually. And of course, the level, we try not to mess with that too much. The stripper level and all that. It's pretty much good. And of course, you have the composition, the initial transient. Like I said, it takes more than some processes take 20 hours or more to even settle down. And we try not to mess with that a lot. And we try not to, this is basically a mistake as well. Yeah, of course. Okay, and of course, the production quality it's not even tampered with actually. And of course, these are the recycled valves. It's very, very small. Like I said, Rika suggested for a mode A that you do not open the valves so much because you don't want too much of that, especially with the steam. It should be kept at 0, which was actually met with our controller. And of course, this is just the set point summary of the EMPC over time. And of course, you have the mean, max, and the observation of the upper bound of that. And then you can see if when you put this together, you see that the major cost for this architecture, actually, it can be different for another architecture. The major cost of the plant is basically purge cost. So in conclusion, basically, just to remarks of what has been done so far. You have what we've done, the scope of the limitation of the studies that the software has been validated. We validated basically the MATLAB model that we're currently using. Mode transition, of course, is not optimized. Mode transition is just from one mode to another mode. Surrogate generalization is part of the scope, but we're still on that actually. Per mode NOx training, which we already did that, but it's part of the scope as well. ECR weight calibration. ECR is just equal constraint relaxation. It's used with the slack variables to keep the slack variables checked in MATLAB basically. And the single mode, NSGA is part of the work, especially for mode A, before we can generalize. And the conclusion is that NOx identification, which the round robin excitation is validated with the NOx model. Of course, we saw that with the results, economic improvements of the mode A, less than 14% less than the baseline. Quality is always preserved actually, which is a primary concern. The NSGA from the study shows possible potential of a reasonable trade-off amongst profit energy, which we are going to explore very soon. And overall, we were able to reduce the average cost. And recommendation, I would recommend most likely that for every simulation, especially when we start testing with disturbance, we run over a 72-hour period rather than short hours. Most simulation would not run this for 72 hours. They will cut it at 40 hours. And I still feel that sometimes when you run the simulation, you'll still experience a little bit of transient taking place actually before it settles down. So 72 hours is good. Coordinated tuning, some persons, tuning the PID might be, you need to know. So I recommend doing a sweep, basically, an EMPC sweep actually, to find what is the possible direction of tuning. So you're very careful with that. Constraint stability, of course, like the inventories has to be stable, and of course, keep the production rate basically. A multi-metric, much more metric than what we have just to evaluate that. Much more statistical metric just to make sure that our strategy is not a fluke and it works out pretty much. So for future work, currently, yes, future work we're currently looking at right now. I wouldn't say future work, I'd say upcoming work right now because the disturbance and noise testing is to test our strategy, especially in wide architecture. When we test it out with the noise to see if our strategy still survives Multi-mode extension is also one of the modes we're trying to consider, between different modes. Energy priority optimization, of course, it's the phase 3, which we're trying to look at. A future work afterward will be to replace the EMPC layer with a surrogate-assisted model. Because optimization online, it's very expensive, actually. Direct purge supervisory action. RICA aligned its control structure to use pressure to control purge, which, from my view, is not always the optimal solution. So I would feel that maybe we can separate purge control to have the EMPC and even the multi-objective layer manipulate purge directly. And mode transition optimization, when you transition from mode A to B, do you get optimal set point, especially when disturbance hits? And of course, these are the complete works, and this is the work in progress actually at the moment. The references and of course acknowledgement. Of course, we're all grateful to the Almighty, Alhamdulillah, that I'm first of all being here in KFUPM. Given the circumstances of how I came here, I don't think I was supposed to be here in the first place. So I'm grateful to Allah for how that happened, inshallah. And I'm grateful to Saudi Arabia as well. I mean, I've had pretty much fun experience since I've been here actually. And of course, the KFUPM, it's been hard, it's been tough actually, but so far, alhamdulillah, I'm here standing and still able to do my defense. And we have the control CIE department. Like I said, I attended the defense yesterday, said it's the best department ever. I agree and I stand to be corrected. It is the best department ever. I mean, if you don't agree, take it up with the dean and other departments. But if you don't agree, anyways. And of course, appreciation. First, I cannot, words will be short of to, express my appreciation to my advisor. I mean, I would say he's the most patient man I've ever seen. I know that I'm someone who would literally poke the bear, but he's been patient every step along the way, very supportive, and he's been patient because I know that what I've done, I should be dealt with seriously. But alhamdulillah, he's been very patient. Dr. Mohammed Sabir, I am grateful because thank you for the problem. Actually, you coined this. It's I'm going through hell, but alhamdulillah, I've learned so much from it, and hopefully that I can become better because I've learned so much in terms of skills using advanced process control. I've been able to attain so much from the problem. Like you said, I remember the first time you said it, you were like, you just told me the name of the problem, and that's it, khalas. Well, you literally did that, actually. Told me the name of the problem, and khalas. That's you've been helpful, actually, very supportive. And Dr. Mahmoud Mujahid, thank you so much. I know we haven't really started or embarked on the NSGA, and I know there's a lot of questions around it, but thank you so much because I know you've always been pushing forward to see how far the progress has been. But inshallah, hopefully, once the phase 2 is finalized, we can move forward. We can move forward on this actually, inshallah, and begin the NSGA section of it. And lastly is to thank my family. My family has been very supportive, especially my mom. She doesn't understand a thing about control, but she keeps on praying and hoping that I can get good results. My friends and family, I mean, I don't know where to start. Abdullah is a brother, basically. That's all you need to know. He's a close brother. Emmanuel, a mentor, I would say. And of course, I have some great friends that are here. Some friends even in other departments that help me in trying to understand, especially when it comes to the chemical part and then understanding the synergies. Friends like Mariam Sami Fargali, thank you very much. You're here today, thank you so much. And of course, every other person that are here to support me today, I'm very, very grateful. Thank you so much for attending the defense. And hopefully there's not enough questions to roast me at the point. Anyways, thank you very much. Appreciate it.
Thank you very much, Fawaz. And now it's the time for questions from audiences here. If you have any questions, we have time for a couple of questions. Yeah, you can challenge him now. Because he will challenge you. Okay?
I haven't gone to the gym in a while, so you can. I haven't gone to the gym, so when I go to the gym and I'm ready, we'll settle scores out.
The ladies at the back. You have any questions?
We don't have any idea about questions.
But did you enjoy?
Okay.
I actually have an inquiry.
Yeah, of course. Go ahead.
And thank you for the wonderful presentation. I would like to understand something. Of course, I'm not from that field, and I want you to elaborate on that sort of work that you're doing. What's the time frame to achieve such a thing? Can you estimate? What are the main challenges?
The main challenge is, first off, any control problem, first challenge is modeling. we've gone through hell in terms of modeling. I've had to change, I searched several models, we've had to change models on the go. So estimating a time frame, hopefully, inshallah, by the end of we can get something very soon, hopefully, inshallah, but it's not necessarily, there's no, but it's a very large, PlantWide control is a very large space. To be honest, this is a work that has been continued. I mean, Skogis has started, Larson entered. So it's a lot, actually. I can't really place a time frame to it. But like I said, main challenges, modeling is one. Tuning of an EMPC is not a day's job. It's not, in fact, in the industry, it requires real skill to be able to even tune an MPC, let alone an economic one at that. So it's not, I can't place a timeline to it, but inshallah, I'll be done. And I will have my master's degree, please.